All right. So there were a couple of questions in last time's class that I needed a little bit more education on. Question about kerosene. Actually, it's been used for more than 1,000 years. There's a report from a Persian chemist and scientist that you could take crude oil and you put it in a flask that is heated, and then you connect it to another flask that is cooled. So there's some pipe, and then here's the second flask that is cooled, and there's like ice around it. I mean, the setup is actually very similar to the kind of stuff that we do today. And I don't know why I chose red for cold. That seems kind of, boom, much better. Yeah, right. In any case, yeah, you can condense, and they needed to do this repeatedly to sort of get rid of all of the other volatile compounds. But what would remain over here is the crude oil and tar, and eventually after multiple cycles of distillation, you can get kerosene as a pure liquid. It is a mixture of hydrocarbons with a particular boiling point. Kerosene is used in jet fuel, lamp fuel, and so on. So there's that. It's kind of interesting. It's sometimes called paraffin oil. I forget. Need to look it up. No, here, no. You've heard me talk about olefins, which are alkenes. Paraffins are saturated hydrocarbons. And if you've ever heard of paraffin wax, it's the stuff that doesn't evaporate but can be separated from crude oil at higher temperatures. Then let's see, octane rating. Still not clear totally on that, other than that combustion engines, at least gasoline combustion engines, involve some kind of cylinder that compresses a mixture of fuel and air, and then there's a spark at the bottom. Spark. This is not a physics class. I'm not really doing great at this. But the mixture of octane isomers, whether that's isooctane, or let's see, is that even 8 carbons? 1, 2, 3, 4, something like that. And then N-octane. Somehow that mixture affects the ability of the fuel to withstand compression. Let's see, if the idea is that you don't want the fuel to ignite until the spark happens. And if it ignites spontaneously because of pressure and temperature as the fuel-air mixture is compressed, that can result in non-uniform ignition, it's the explosion that pushes back that cylinder that turns the engine. And if the combustion doesn't happen with the spark, but happens a little bit before the spark, that gets off the timing of the engine. That can result in knocking and or pinging. And octane rating became important during the early years of air flight, where the ability to get consistent compression at multiple altitudes was important. Octane rating may or may not relate to engine efficiency. It depends on how your engine is designed. What that means is probably if you're driving a regular car, buying premium fuel is a way to throw away money to demonstrate one's privilege, but other than that, probably doesn't influence your car efficiency. So there you go. Sorry, that got needlessly political. If you love to buy premium fuel, more power to you. But it has a higher octane rating, and that's related to the mixture of octane isomers. And I don't know physically why changing that mixture influences how well the fuel can withstand compression. Likely has to do with differences in boiling point, but there you go. All right, well, that's that. We are talking about, see, anything else? Anything else you want to know? No? Tons of things, but not right now. All right, fair enough. Right, so we've been talking about reduction reactions. We've talked about turning alkanes through hydrogenation over palladium on carbon to become, olefins to hydrocarbons. We've also talked about alkynes, and there's some important stuff from last time where you needed to be able to use your knowledge of stereochemistry and your knowledge of alkyne reduction conditions, either the so-called dissolving metal reduction or the Lindlar catalyst, to get cis or trans olefins respectively. The one last reducing agent that we need to introduce, and there's a whole host of reduction reactions that you can do. Oh, I'm kind of all over the place, but sorry, we're going to pause. Did you note how these reactions involved addition of hydrogen across a double bond? You added 2 protons and 2 electrons. You can think of, and let me see if I've got in my notes here, you can think of adding 2 protons and 2 electrons in multiple ways. It could be separately 2 protons plus 2 electrons. It could be 1 hydride and 1 proton, and then it could just be adding hydrogen. And all of these approaches are used in various reactions and in nature. In fact, enzymes that are involved in oxidation and reduction reactions, it's interesting, enzyme catalysts don't care about thermodynamics. They don't care if the reaction's downhill or uphill. They just change the mechanism. And so sometimes it's unclear whether you should name the enzyme according to the forward or the reverse reaction, so biologists just pick one. And then sometimes the name describes the backwards reaction versus the one you're actually trying to do. A lot of enzymes that do oxidations are called dehydrogenases, because oxidation formally involves, of organic molecules, involves removing 2 protons and 2 electrons, or 1 equivalent of hydrogen. So it's an enzyme that dehydrogens a particular molecule. And annoyingly, the reduction enzymes are often also named dehydrogenases for the backwards reaction. So you'll hear that kind of thing in biochemistry. Is that going to be on the test? I don't know. That's unsettling. Well, sorry, welcome to adulthood. It's just unsettling. No, but you should know what oxidation and reduction is: increase in the number of carbon-hydrogen bonds, or for reduction, decrease in the number of carbon-hydrogen bonds for an oxidation. So one last reducing reagent that we need to introduce is the aluminum and borohydride reducing agents. So this is the borohydride anion. Boron, when it's bonded to 4 things, has to have a negative formal charge. Sodium is usually the counter ion. And then you also have, from the same column of the periodic table, aluminum hydride, which is more reactive. Its counter ion is typically lithium. Don't know why the change in counter ion. These are reducing reagents. You might imagine that one way to do a reducing reaction, say, suppose you wanted to reduce an epoxide to the alcohol, and you wanted to basically add H- as a nucleophile, open up the epoxide to get a negatively charged intermediate, which you could then add a proton from some aqueous workup. Oh boy, try that again. To get the alcohol. By the way, do you see the addition of hydride and then proton in separate steps? That's sort of a pattern for reduction reactions involving a lot of reagents. The problem is that hydride H-, there actually are reagents that are H-, but one is called sodium hydride. It is an inorganic salt and is not soluble in a lot of organic solvents. So basically it sits as a chunk of solid at the bottom of your flask, and individual hydride atoms are not released into the solution. In fact, at best, this sodium hydride basically is this very large chunk that has highly basic stuff on the surface. So sodium hydride is really good at deprotonating things, but it's a terrible way to deliver H minus. So we need a better way to do that, and the solution to all of that is these borohydride reducing reagents. Effectively, they are hydride carriers. And the strategy actually is used by nature too, though not by these particular reagents, but nature has a couple of reagents that are hydride carriers. NADH, if you've ever heard of that, or FADH2 are both hydride carriers. So how do these things carry hydrides? Well, first, you know that there's you can have a boron that's attached to 3 different things with an empty p orbital, and it's neutral. So it should sort of make sense that losing a hydride should be possible, because you go from something that's negatively charged to something that's neutral. The other clue as to why these are hydride delivery reagents is because the electronegativity of boron is actually less than the electronegativity of hydrogen. So what that means is, though we've got a negative formal charge on the boron, actually most of that is shared out on these hydrogens. So BH4, and also same thing with Al4 minus, is a carrier, has partially negatively charged nucleophilic hydrogens. And the electronegativity difference is bigger between aluminum and hydrogen than it is between boron and hydrogen. So lithium aluminum hydride is more reactive. Now you're going to use these mostly in 352. The one reaction I'm going to show you that you can do with this is called epoxide reduction. And I'm going to allow you to use either of these reagents interchangeably. In terms of epoxide opening, let's see. Here's how it goes. We'll use lithium aluminum hydride. Lithium is just the counter ion. The reaction is going to proceed as though the hydride that's delivered is a strong nucleophile. So in terms of epoxide opening regioselectivity, the usual issues apply. Sterics matter more, the strong nucleophile will attack the less substituted carbon. And what you do is you just simply show the hydrogen taking its electrons and leaving and attacking the epoxide. It's not leaving really and floating around in solution, it's more of a direct handoff. And then we break the carbon oxygen bond. The new hydrogen is delivered here. We can't tell, but if the stereochemical issues were different, we'd be able to see that there was definitely backside attack. You get the negatively charged intermediate, and then after aqueous workup, you would get, I mean, that's kind of an expensive way to make tert butanol, but that's the idea. You can use lithium aluminum hydride to reduce epoxides. And in so doing, all the same issues with epoxide opening apply. So if we had our sort of favorite epoxide situation, and you used lithium aluminum hydride, after aqueous workup, you would get the following product. And let's go ahead and put a deuterium here so that we can tell that backside attack occurred. Sometimes people like to be cute and use a deuterated hydride equivalent, so you can buy ALD4 lithium aluminum deuteride, I guess, where instead of hydrogens you have deuteriums, and then that's another way to prove that you get backside attack. If you ever see something like this, don't worry about it. D just means deuterium, and it just means somebody's trying to keep track of where the hydrogens go. All right, anything you want to ask about that? Yeah? Less substituted carbon. Yep, usual issues apply. Usual regioselectivity and stereochemical issues apply. Right, others? Okay, good. Well, let's talk oxidation. There's probably three reactions we want to introduce. One is making an epoxide. This is one you're going to want to pay attention to because it expands, making an epoxide, it's lovely. It expands your synthetic toolbox. So we already know, though maybe you didn't know it, one way to make an epoxide from an olefin. And the way that we already know is to take the olefin, form a halohydrin by reacting with bromine in water so that you get this 1,2 alcohol/bromide substitution pattern. And then in a second step, you add the strong base but terrible nucleophile because it's insoluble sodium hydride. That removes a proton from the alcohol, which then immediately does an intramolecular backside attack substitution reaction to give you the epoxide. B here is just some base, because I didn't want to draw the large chunk of sodium hydride. That's one way, but that's a two-step reaction series, and we're now going to learn a one-step reaction series. What I'm going to show you is actually used almost exclusively now and not this approach, because it's in one step, because the reagents are easier to deal with than bromine. The reagent is called MCPBA. This part of the semester will have seemed like alphabet soup. That being said, if you wanted to, you could write out metachloroperoxybenzoic acid, but nobody's ever taken me up on that. This reagent looks like what I'm going to draw now. Here's a benzene ring, here's a chlorine, here's the peroxy acid portion. This is a new functional group, one that you won't have seen before. You've seen perhaps peroxide in Gen Chem, and it's got a bond between two oxygens. You've seen carboxylic acids before. So the peroxy acid is a combination of a peroxide and an acid. Instead of having an OH here, we've got another oxygen-oxygen bond and then an OH out here. And one thing to know in organic chemistry, oxidizing reagents often have what we're going to call weak heteroatom sigma bonds. So weak oxygen-oxygen bonds. If you look up the bond strength for an oxygen-oxygen bond, sigma bond, it's relatively weak. And so MCPBA will take this oxygen and will install it as an epoxide with making a bond with both of the carbons of the olefin. If you of course, don't need to memorize this reagent, and frankly, there's nothing magical about this portion of the molecule. You can just use an R group to indicate all of that. So how does this work? It's a single step, and there's a lot of things that appear to be going on in the same step. I'm going to show you the mechanism, and I might ask you about it, but you shouldn't panic because it's not that bad if you pay attention to all the things that have to happen. And I guess I would say after the fact, a byproduct that we typically don't worry about because it's easy to separate out is just the metachlorobenzoic acid. All right, so how does all that happen? Well, let's draw the alkene as though it were sitting here, and we're looking at it on its side. And then we would say that the HOMO of this alkene is the pi electrons, so they're going to be the nucleophile. you would expect them to be able to attack from above or below the plane that holds this molecule. So this represents the plane of the sigma bonds for this molecule. Maybe the dashes and wedges are confusing now. All of the sigma bonds are in this plane that we've identified. Then the peroxy acid orients itself towards the molecule like this. I've drawn it this way because a lot of things are going to happen, and eventually this oxygen in the double bond is actually going to get bonded to this hydrogen. All right, so I told you that the oxygen-oxygen sigma bond was particularly weak. Therefore, the nucleophile is going to attack the oxygen-oxygen sigma star. Okay, so that's one thing that happens. Let's draw here. That breaks the oxygen-oxygen bond. If we stopped sort of there, we would have a negatively charged oxygen conjugated to an oxygen with a pi bond. So actually we can swing these electrons up and break the pi bond and move them onto that oxygen. Then lone pairs can remove this proton from this oxygen. That kind of thing is allowed in OChem because it occurs via a 5-membered ring transition state, and 5-membered rings aren't particularly strained, so that kind of stuff works. And then finally, the lone pair, just as with the bromination of alkenes reaction, the lone pair on the oxygen that got attacked is going to make a bond with the other carbon, and that will give you your epoxide product. And the mechanism's kind of cute because it takes care of all of the proton transfer stuff in the same basic step. So you can see after the fact, everything's basically where it was over here, only we've changed who's bonded to whom. All right. People call this sometimes a butterfly mechanism because if you do that and then you relax your eyes a little bit and then he's an angry butterfly. So that may or may not help you remember things, but sometimes people talk about it that way. Let's see. I just learned the double tap undo trick. Oh, too much undoing. I think, let's see, there's any questions you want to ask about that? I think there's maybe an animation we can look at that'll show this. I'm not sure though. You want to see the animation? Where does it start? Uh-oh. Updating. Who said that it could update? I probably agreed to that at some point. Where does it start? In a reaction where all these things are happening at once. Who asked? Sorry, who am I looking at? Yeah. In a reaction where all these things happen at once, knowing which one started it. But probably I like to think it's the nucleophile doing the attacking, and then everything else that happens is a response to that. Let's see what the animation tells us. Addition to alkene addition, nope. Let's see, oxidation. Oh, there it is. Okay, so here is trans 2-butene, and then here's your peroxy acid. In this simulation, let's see, I need the, nope, nowhere to be seen, laser pointer. Oh, good. Folks watching the recording, I'm using the laser pointer, so you should have been here. This is where the benzene ring would have been. This is the weak oxygen-oxygen bond. Here's the carbon-oxygen double bond. Here's the proton. Here's the double bond of the ring. So we can skip ahead to the transition state. And you can sort of see what's going on in that transition state. You have attack of the alkene to make a new carbon-oxygen bond. And both of these bonds, let's see, we can measure both of those bonds, 2 angstroms, and this is about 2 angstroms. So they're similarly formed in the transition state. That means that this business of who does the attacking first doesn't matter. They're both done to a similar extent in the transition state. And then in the other parts of the transition state, here's the breaking of the oxygen-oxygen bond. Here's the making of a new oxygen-carbon pi bond. Here is formation of a new oxygen-hydrogen sigma bond. Of all of the bonds that are formed, perhaps it's this proton transfer that's least done during the transition state. So let's see. Oh, it's also kind of interesting. Let's see now. Probably there's actually an internal hydrogen bond there that's sort of keeping the molecule spring-loaded in the right shape. That looks like the first thing to happen is the carbon of the oxygen hydrogen bond breaks, and the oxygen-oxygen bond breaks, and just about there where the transition state is, we form the bonds with the epoxide, and then everything swims away happy. Oh, that's okay. Okay. Anything? See, it's just literally a handoff. We're going to do that the whole time. Anything else you want to see? Yeah.
Just want to make sure I'm understanding the double bond on the oxygen switches over to the other oxygen.
Yep.
Will that ever matter as far as stereochemistry if the R group has some kind of stereochemistry?
Will that ever matter? No, because which oxygen has the hydrogen? I mean, probably this thing's getting deprotonated and reprotonated anyway. In the conjugate base, those 2 oxygens are identical. There's no stereocenter here to worry about, so no, won't matter. What else? All right. There are a lot of mechanisms like this that have a lot of arrows, but they're just one step. And so actually answering multiple choice questions about that mechanism is probably going to be pretty straightforward. All right, now you have an interesting way of making an epoxide. So I can make your lives a little bit more miserable than they currently are. That's a lovely thought, isn't it? Actually it's fun, right? I'm sorry, I'm sounding evil today. So now instead of doing, say, anti-addition of Br2, we could do MCPBA to make the epoxide. Drawing an epoxide from this perspective is a little bit tricky. If you want, you can try to do it like this. That's kind of ugly, or you could draw it like this, and that would be fine too. If it's chiral, you get both enantiomers. From the cis olefin, you would get the cis epoxide. Which is not chiral. But likely, since we already know some things, reactions to do with epoxides, likely I'm not going to give you that as your starting or rather endpoint for a synthesis. Instead, I might do something like this. And I might even do something like, which of these is chiral? You'd have to think through, hint it's the one on the bottom, but I'll just write that note there in case you want to go back. The dastardly deed actually would be to take some alkyne and then show you a particular, I'm going to get rid of that, show you a particular or show you a particular diol product, and then ask you, how did we get from here to here? And along the way, you would need to realize that you could get this diol. I'm also evil because I drew the diol product in a way that would make it difficult for you to see that this was a anti-addition, or rather opening of an epoxide from the back side. Those two are the same. You've got to put that there. These are the same thing. So you would have to look at that, think about rearranging it so the OHs were on opposite sides of the molecule, use that to infer what kind of epoxide you made, use that to infer what the stereochemistry of the olefin should have been, and then use that to determine which of your two alkyne reduction methods you should have used. Yeah?
What's the reagent that turns the epoxide into the diol?
Oh yeah, opening of epoxide with just hydroxide and water. Or you could do it under acidic conditions too, doesn't actually matter. Doesn't matter which carbon gets attacked here because both of them, there's no regioselectivity issues, both of them get the OH group. Okay, I'm feeling like I lost some of you on that, or rather that we got to the point of despair rather than the point of like, I can do this. This is true? Okay. This is the way. Yeah. So let me try to walk you through it, okay? Step by step. Here's your starting point. Here is your ending point. And I will be nice in the, well, nice is, I guess, relative. I'm going to show you multiple ways I could have drawn this product. And I would have said that you get both enantiomers. So some of you forget occasionally that you can rotate around carbon-carbon bonds. I'm disclosing one of my evil tricks, which is to show molecules in different conformations that make the answer less obvious. So don't forget you can rotate around carbon-carbon sigma bonds. All right. So what am I going to do here? Well, I'm starting with, I've got an alkyne starting point, I've got a 1,2 diol product. And it can be good if you have the patience for it to sort of write down the structural patterns. That may help you remember reactions. So the first thing I need to be thinking is 1,2 diol. There is a reaction I've done before where the 1,2 diol is the product. This is where, if you haven't already done so, making a flashcard or something where you have a 1,2 diol product and you ask, how on earth did I get there? That can help you remember, or at least be familiar with what the tools in your toolbox are. Because that's essentially the question we're asking here. So the only 1,2 diols we've made before have been made from opening of epoxides. Okay, are you okay with that connection? That is a chapter 9 reaction, which you can't forget about. So, I mean you can, but you must not, I suppose. Okay, so I'm going to write down here epoxide opening, and the reagent for that is using hydroxide and water, or I could have used acid and water. It's important for me to know because this is an epoxide opening, it's important for me to know that the mechanism is SN2 and proceeds via backside attack. Because stereochemistry matters. I didn't show you any other stereoisomers. So you gotta be paying attention because the stereochemistry of the product in epoxide opening, a stereospecific reaction, is controlled by the stereochemistry of the starting material. All right, so if we redraw this molecule such that you can see where the OHs would have been via backside attack, what is the epoxide I should have started with? Okay, now let's try it in the forward direction just to make sure we're not making stuff up. This is one way you can check yourself as you're planning a synthesis. Just check and see, did what I just proposed work? Does what I just proposed work? Excuse me. Opening of either of these carbons, A or B, has to be done at the same rate because they're identical. I'm going to just show one. If I did that after aqueous workup, let's see, stereocenter A remains the same. Stereocenter B should, from our perspective, inversion means that the wedge here and the dash for the methyl group were oriented downward towards the bottom of the page. Now they're going to be oriented upward towards the top of the page. So let me ask you again, is that the right epoxide? No, okay? It's not, because backside attack opening of this epoxide does not give you the desired product, okay? That's a key thing that you will need to successfully answer questions of this nature. So let's try the other epoxide, A and B, where the methyl group is here. Then let's try this in the forward direction. Opening of the epoxide, backside attack. I'm not showing you the subsequent aqueous workup step. Stereocenter A remains unchanged. Stereocenter B, we had the methyl group coming out towards us, the hydrogen going out back away from us, but both are angled towards the bottom of the page. Inversion of configuration here means that they'll now be angled towards the top of the page. Okay? Anything you want to understand better there? That's the right one, yeah. That's right. You're looking for the synthesis, and this is the right one. I'm going to say it all the time. This is the way. Okay, now making an epoxide. You can use any method that works, but the easiest one is the MCPBA reaction. And notice that because the MCPBA reaction is concerted, there is no time for rotation around there's no ability to rotate around the bond between carbons A and B during the transition state, because you form both of these bonds at the same time. Epoxide formation is like syn addition of the same atom to both carbons of the olefin. So stereochemistry of the olefin is reflected in stereochemistry of the epoxide. That is, the groups that are cis in the epoxide must have been cis in the olefin starting material. Cis, cis. Concerted, we'll call this syn addition. All right? Pseudo-syn addition, because we're not actually adding two things, we're adding one thing to both carbons. Okay, so if I want to use MCPBA, McPuba, you guys like to pronounce this, I've heard people say pockle and sockle, so it sounds maybe like can we think of a McDonald's product? I want a McPBA, please. Should we just, yeah, we're going to start something new. All my organic colleagues call this MCPBA, but we're going to call it McPBA, okay? So, what's the stereochemistry of my alkene? What does it have to be? Cis. Okay, and now I have two methods for reducing the alkyne. I have Lindlar catalyst or sodium dissolving metal reduction. This is like that scene in, is it the Minions movie where they're trying to convince Gru to be evil again and they're showing him with weapons and things, yay, and then doing altruistic things. Yeah, which one is it? You voted with your yays. It's not this one. It's this one, hydrogen and the Lindlar catalyst. Now, if you wanted to get the other stereochemistry, then just use, actually we've drawn it up above, so if you wanted to get the other stereochemistry, everything stays the same, only you make the trans olefin instead of the cis. Okay, let's see, another evil, so that's this series of reactions actually, epoxide opening followed by, or epoxide formation followed by epoxide opening. This two-step sequence of reactions here, starting with the cis olefin, starting with the olefin, your text calls that anti-dihydroxylation. I don't know that I find it useful to call that something else. It's epoxide formation followed by epoxide opening with OH minus. But the net effect overall, and you can see why they're calling it anti-dihydroxylation, is that relative to the original structure of the alkene, the OHs end up anti to each other. So if this were a single step reaction to make the diol, we would call it an anti-dihydroxylation. Organic chemists like options, so we actually have a method for syn dihydroxylation. It also involves a weird reagent that has a transition metal in it. We will not be worrying about the mechanism, though I'll show you some mechanistic steps just to help you feel a little bit more comfortable with this. The reagent is osmium tetroxide. This is a highly oxidized form of osmium, which is a transition metal. And so breaking of any of these oxygen-osmium bonds is thermodynamically favorable. If you bring in, let's see, again in the plane that I'm drawing, let's start with the cis olefin. Syn dihydroxylation delivers two oxygens to either of the carbons of the olefin, A and B, and does so on the same side of the molecule. I'm going to draw some arrows here just so you have a feel for what's going on, but I won't ask you to draw a mechanism for this reaction. The pi bonds attack one of the oxygens, electrons go back onto the metal, and then these electrons from this metal oxygen bond attack the other carbon. And you end up with a 5-membered ring intermediate where the two oxygens were both added to the same side of the original olefin. This intermediate is called an osmolate ester, and usually that's opened up with water and a particular salt, and I forget which one it is. I think it's that one. It doesn't matter, and your text never explains it, just is using conditions that work. That gives you overall syn addition. So you take the cis alkene and you use osmium tetroxide, and then you break up the osmolate ester. Some of you are going to be troubled by this. I'm never going to make a distinction where if you forget about this second step, you get a question wrong. All you need to remember here is the osmium tetroxide bit. But it forms a 1,2 diol, but with syn addition. So now, just to make matters worse, stop it. We could now start with the trans olefin and get to this product, or in other words, sure. Through these reaction conditions. So if you look above, in order to get this diol, we used sort of anti-dihydroxylation. We took the cis olefin, we used MCPBA, then we opened up the epoxide and we got that stereochemistry of product. Now we have a method that can start at the opposite place with the trans olefin and get you there, right? It's terrible, isn't it? That is a lovely interchange of mechanistic detail and stereochemical detail that you really ought to put some thought into, because I always ask questions about it on the exam. Yeah?
So the anti-dihydrogenase.
Yes.
When it's used on the trans, it should give us
The question is related. In fact, let's cover that again next time, if that's okay.
With the osmium tetraoxide.
Yep.
With the trans alkene, does it not introduce in addition to
Yes, absolutely.
so how can you get two products out of that?
These are the same thing that just rotated. I fooled you again, didn't I?
I guess I
Sorry, I didn't mean to laugh. That was an evil laugh. Yeah. Okay. Hey.
What point is, so I'm starting to kind of take studying with all the mechanisms and stuff. At what point is having the mechanisms like memorized, understanding them well, going to help with synthesis? Like,